Hello again. Um, just a minute. Okay, I just wanted to finish this up before returning to the other thing, the COM and aggregation stuff, which is starting to, the pieces are all starting to fall together as it turns out, and I think I have a way of looking at aggregation using just C++. That's analogous to COM aggregation. Anyway, not the topic here. Here is the topic is our this default constructor trick hack that I mentioned. And I was just starting to go through this stack trace and show you how that worked. It's a build. You may have seen this sort of thing before. First, there's something, this line right here that I've been saying over and over again. I was going to explain how this works. So here's a perfect opportunity anyway for me to explain, well, first what this function says and what it is, and secondly how it works. What this AddressToHinst says is the following. Again, a picture will help. In your processes universe, okay? So the universe of a process. Each process gets its own universe, as you probably know, all to itself. You know, it has its own copy of the operating system, everything special and unique to that process, as if there were no other processes running at all, almost like a single task environment. There are threads, but there's just the one task in the address space, what I call the address space of a given process. Okay, but the process itself, the exe module, okay, is like a program, you know, an exe file. And what happens is that program gets loaded into memory at a given offset. So I should actually say where this is. It's at, I think that's the number, 60. At this address, 0 might be up here, and all the way down at the bottom is the maximum possible address, 4 gigs. Now what's wrong? X. Right? 1, 2, 3, 4. 1, 2, 3, 4. And this has 7, so really I could write it this way. Now sometimes people like to view memory as increasing in a downwards direction. Perhaps it would be better to do it upside down. Simplicity. So let me put 0 on the bottom. Zero. take this and put it on top. That's the highest position in memory. And that 0 is going to disappear. But I'll get it back. Come on back. There it is. So you could think of this as the layout of all memory. Okay. Now maybe I'll make a little. I can't do arrows apparently. I probably can, but I could also do it across. Another maybe more convenient way to draw it is horizontally, but I'll do it this way. Now this is a linear, as I've said before, flat memory model in which all addresses are within this range and specified by a 32-bit number in Win32. And that gives you 4 gigabytes worth of positions, valid positions, okay? But the way it's organized, there's a granularity, of course, and the granularity happens to be 4 kilobytes in this model, in this Win32 model. But that's not important. So your exe module, the base address, the lowest possible address where it's loaded is here. Is it 4? The right number of zeros. This is 4, 4. 1, 2, 3. Oh no, 5 zeros. Okay. And if your program is, let's say, 2 megabytes, if it's image, I should say, that's different than the size of the program, the file. If its image in memory is, let's say, 2 million bytes. Now let's see, what is that in hex? 1 million. Now why do you do that? It's funny, I see. Because the other one's currently blue, I think. But 2 hex. 1, 2, 3, 4, 5, 6. Is that, which is nearly F, 5 digits worth of F, so it's approximately 6, no, it can't be. One, two, three. Oh yeah, okay. Like this, right? That's one more digit. Yeah. Okay, that's convenient because this has 5 zeros here. So if it was a 1 megabyte or 2 megabytes, we can just put that number here. Let's say it's 1 megabyte, so the top. The highest position in your exe module, which I'm going to illustrate as a box. Is there. Just to give you a visual feel for it. Okay. Now, when a program runs. Typically, like you can see listed here, a bunch of other things called dynamic link libraries get loaded into the same address space as your process, but they're visible to you, like the runtime library and kernel 32, the operating system, and various. Here's the C runtime. Here's GDI for drawing things, and various other things. Sometimes more things will get loaded later on. Well, you'll notice that these things happen to be way up near the top. In fact, the highest available address is not FFFFF. You're not allowed to. You can't put a program there. The highest possible address where you're allowed to put a program is almost exactly half the distance from bottom to top. So if this were 7FFF, okay, you could put a program here, well, one byte less maybe, but not on the next line. And the reasons are the same reasons as I explained in DOS, and it has to do with the granularity and the maximum possible addressable offset that you can go to by a call or a jump, such that you don't wrap around. Okay, if you have a program here above this value, it's possible for you to make a call that you intended to go here, but really it wraps around because of this sign thing. Exactly the same as I explained many months ago, maybe a year ago, in DOS. All these different modules, especially the kernel and all those other ones. In fact, this is really way, my box here is way too big. It should be more like that. Okay. Those things are all up near here. A whole bunch of modules, and I'll just draw a few boxes to represent them. Well, there's no second dimension here. There's only one dimension. So the box is only drawn as a two-dimensional figure for convenience. That's not the way things are. Things are linear. This might be kernel 32, let's say. Oops. Okay, so this is my program. So I'm going to imagine that, let's say that the top here is 7FF. So I can put some more in. I don't know. Wow. Okay, just for making things up. Another one in that list was shell 32, right? I don't need more than one bar. and so on. Okay. Now, your program, as it starts up, also allocates memory. For the various heaps, I talked about before, the dynamic heaps, right? Those are the things that you would call static cast to retrieve, the things that are in the dynamic heap. Just remember, everything's backwards. For instance, one of the dynamic heaps is called the stack. It happens to be exactly 1 meg big, almost exactly. It doesn't have any module name or anything. It was allocated by this program, but it's not based within the program's area, memory. It's based down here. I should center that. And it's 1 meg, and it grows down. And the address of the stack, I think, is 1 2. Typically, is 1 2 something. Oh, let's see. Can I see anything in here? Let's put a breakpoint somewhere. Something on the stack would be here. Now that's got 1 2 3 4, same number of digits, and 1 2 FEE8. Okay. Now the top happens to be 1 2. Am I printing it in this case? I print out the heaps, not by default, but I can turn it on. What's our program called? Delegate, right? How come I've only got 1 here? Because they go in here now. That's why. Dump heaps. So if I run up to here again, we should get a printout of the heaps in this box. Here they are. The stack is going to be 1 2 something. Here it is. So 1 2 D 0 0 0 should be the top of the stack. Okay, this is higher up in memory, so that's not stack. Well, it should be. Oh, last block. How big is 1 block? Okay, so it doesn't show us the top. It's showing us the lowest address of the last block, and the size of each block is how much. Commit size. Well, it's probably it's got to fit this one in, and this is nearly 1 3, right? So I'm imagining that 1 block is probably 3000 hex. It could be more. But in any case, this number will get smaller and smaller and smaller as you add things to the stack. And when you hit the bottom, right, of the stack, it can grow itself, but eventually you're going to hit 0, and then you're dead. That's a stack overrun. If you want, you can have a much bigger stack than 1 meg. You can specify that in the compile settings. Well, then it can't put it down there. It's got to put it somewhere else because there's not enough room. There might not be enough room if you specify a huge number, as I'm going to do right now. Reserve 1, 2, 3, 4, 5, 6. So that's 20 million instead of 1 million. You're going to see that those stack things, the stack is going to be in a different spot. When I run up to this address, this will not have the same kind of value as before. It's this great big number, right? It's another digit increased by an order of magnitude. But actually, it's still below the program image, right? Yeah. It's at 1.8. Well, let's see where it is. Here it is. It must be it. Because last time it was the first entry. So 1.6 up to 1.8, the chunk size must be to 20,000 hex. That's a 20,000. That makes sense. The last block, meaning as you're going down, I guess, would be there. You can't put one. You certainly can't put one if this block size is this. You can't add another block, or else you'd be at 0. Oh no, but here's another one. That's the same. Oh, I'm not sure. Now these other ones are way up, 1,000,000 miles away, right? This is probably from Alex. These 24 things. I'd have to do a malloc to see where in memory it comes from. Well, I'm sure we'll run into a malloc. Definitely in this print. But anyway, back to the stack walk. We went through this. We got the address of the caller and the correct name init outer. Now what we're doing is we're doing a stack walk, which means that we're taking the EBP register, right, and dereferencing it over and over and over again. Each time you do that, you end up at a new stack frame where everything is true, but in the context of a further up function. Everything that is true in terms of the logic of the stack is true, but we're in a different context. But the first thing I want to check to make sure of is if that return pointer, okay, well, it's not going to be somewhere on the stack. That's not code. This here is code, right? I'm not allowed to store data in here. These two, where all these DLLs are also code. If it turns out that the return address happens to be in kernel 32.dll, right, from some function, then first off, I'm not allowed to look in there, right? I can only guess. I mean, I can see a little. You can see a little bit, but I don't know which function's which. by its address, and eventually it's going to stop using the convention, the stack frame convention, and everything is just going to stop. So one way to see whether or not we've landed in either kernel or shell 32 or one of these other DLLs is to see if the return address happens to be within our executable modules area. This is a fixed thing. It never changes. You would have to go through great extremes to alter the program's image in memory, increase it or decrease its size or move it or something. Nobody does that. But in any case, it wouldn't change this logic. What I would like to know is which module, right, this address, whatever it is, that's returned from this function, which module is that in? And the way to find that out is by walking the memory, all memory, from 0 up, okay, and locating the positions in memory where every module is. Okay. All right. Now that's how this was generated. See this list here? This is not coming from the runtime library. I'm printing this one out. These are the modules that I found loaded in memory by doing a module walk, and that's how this function works. It does a module walk and finds out, which of the modules in memory there are. This address is within. It has to be within some module, because in order to make a region of memory available such that you can put code in it and run that code, you have to allocate a region of memory. And each of those regions of memory are distinct, and they all have corresponding files. Okay, it would be possible to make one that has no file name. It's possible, and in fact, this function I don't think checks the file name. All this function does is return the base address of the region of memory that this address is within. Now, get module handle returns the base address of our program, so it would return this number. So for any address, if I took any address in the program and pass that to this function, it's going to return the number for 400,000. Okay, every number. Similarly, any position in this module, for every position in this module, this function will return, which one is that? Kernel 32. It'll return 75BD00000. Okay. Now, if the return address, we're going through a loop here, starting at 2. If the return address of the use caller happens to not be within this module, then there's no possibility that we issued the call, because we issued the call and that's all happening within this module. So therefore, this check tells us that it's time to quit. We can, there's no more searching to do, and we're done. Okay. Long explanation. Now I'll show you how this works. Oh dear, I just stepped over it. Put a breakpoint here. Do it again. Get in there eventually. Alright, here's an address being passed. It's obviously it's going to be within this module, but we don't know that. The function doesn't know. Now, what's this? Okay, this is the case where someone passes in null, and this function is designed to give you the H instance of the current module in that case. So, right, address to H instance of return address. Never mind. Current module. It doesn't have to be an executable. It could be a DLL. The way this works is using a function called VirtualQuery. It's a very useful function. All of this memory is virtual, as you probably know. Virtual memory in the sense that there really is no 4 gigs layout of memory. These addresses are all fake, and they might point anywhere. They might point to files on the disk, but we imagine it as a flat region of contiguous RAM memory. But it is virtual memory, so in order to find out about that virtual memory, we can use this virtual query, which I just press the help on. Okay, there's an extended version too. Provides information about a range of pages. Okay, now a page is the granularity 4 kilobytes I told you about before. In the virtual address space of the calling process. Okay, that's depicted here. This is the virtual address space of a process. In this case, the process program exe. These are not processes, they're called modules. Alright, well, it's easier to step through it. P here is just a pointer. Starting out at 0, okay? So we're starting out with a null pointer. And we're doing a loop while the current pointer we're looking at is less than the one passed in. Okay? Makes sense? You'll see why it's not less than or equal to or something in a minute. And now we're querying this pointer and finding out information about it, which is returned in this type of structure. It tells you the base address for the pointer, allocation base, something about the protection, size of the region, and some things about the state of the region. Okay. Now, why? Okay. It is supposed, this function returns the amount of data copied into this buffer, and if it fails, then this equality would not be true. According to the help, return value, number of bytes returned in the information buffer. The number of bytes ought to be equal to the size of the buffer. That's what this says. So on F10, okay, it did copy some information in the buffer. So here it is. So for base address 0, null. Its allocation base is 0. Protect flags are 0. I'm not sure what that means. The size of the region is 10,000 hex. Okay, which is decimal. I think we said that was approximately 1,000,000. Oh no, sorry, 10,000. That's only 64K. Yeah, sorry. It was 100,000 is 1,000,000. Okay, so it's 64. The region is 64K big. Protect 1. I think protection 1. There's a number defined for it. Let's see what the protect values can be. Page guard or page no cache. Okay, 1 is no access. Okay, so this particular page at 0, and you've probably learned this yourself by typical accident, trying to dereference a null pointer, that this region of memory is marked as no access for one DOS segment worth of memory, 64 kilobytes, and everything else is 0. Okay. So now what am I checking here? If it's not free mem, let's see, state. Well, it's not going to be anything at all. Free mem is this flag from state. State happens to be, say, free, turns out. Oh wait, hang on. This indicates free page is not accessible to process but available to be allocated for free pages information. Okay. In allocation base, after check, etc. are under. Oh, that's funny. Am I reading this right? State, right? This says free. Not accessible. So anything that is of this type, we can ignore these flags, right? The information in these flags, like type and protect, we can ignore. All right. So this, although this memory is unusable, we could allocate it. So if you wanted to, you could allocate this and use 0 as a valid pointer in your program. And maybe that would be fun. You could impress your friends by you know, setting a pointer equal to null and then assigning some values there. You probably shouldn't, but definitely you have to do it for fun. It's not equal to free. Well, it happens to be equal to free, so this condition immediately fails. Notice that the order of tests here, this has to be tested first, because these other things are, if this is the case, then these other members are not valid values. So we failed on the first one. So what do? Region size is valid, right? It's only these ones that are invalid. We jump to the next region by region size, which is this 54K, into the next region. So now P is here. Now we're reading. It's reading memory here. So obviously this one is valid, right? It's not saying invalid pointer or anything like that. Okay. Oh no, now okay. But still, we're reading it. Now we call query. This one says, here's the base. Size is the same size as the last one. Oh, but it's free, so we can ignore all these flags. They have no meaning. Strangely enough, though, we're not getting an access violation in reading it. I mean, the debugger is telling us that there's memory there, right? See? Am I right with the flag? Yeah. Again, going back to the help. Not accessible. Well, that's not true. We are accessing it. Indicates free pages not accessible to time process and available to be allocated. You got me. This is, we're reading this memory. I guess what they mean is you can't trust it until you actually allocated it, and you can't trust these flags. What is for? For protect for read write. Seems like these flags are being applied, even though the help says that they aren't. This is Win 7. Maybe they changed something. Okay. Oh, it wasn't equal to mem3. What was mem3? One followed by 4 0. Oh, this is only 3 0. Okay. What's this state? Commit. Okay. So we found a region at 10,000 that has been allocated, so now the flags are valid. Its size again is 64K. Its type is for this. It's mapped. Okay, it's mapped memory. So that's like when you do a file mapping. Indicates pages are mapped into the view. So it doesn't have to be a file. When okay, I don't know the difference between a section and an image section. Private, not shared. Okay. So you can have private memory, mem mapped, which is mapped into the view of a section, and an image section, which I don't know what that means. Not important. All I'm doing here now, I am actually getting the module file names. Why am I getting the module file name? I don't need to. Oh, I remember. Yeah. The return value of this function, if it's non-zero, right? If it's non-zero, then that tells you that the allocation base member of that struct would be the H instance if it were a file, let's say, corresponding to that region of memory. It doesn't have to be, because sometimes there are subregions, if you know what I mean. See, look, the path length here I'm giving is only 10 characters. I'm not trying to find out the name of any module, only to see if this thing returns some numbers. If it doesn't return a number of characters, it should return up to 10, then that means that this region of memory does not have an associated file, and so therefore it doesn't correspond to any executable module. Okay, that's what we're looking for. So this should return 0, and we're going to skip over it. We do. Jump to the next region and just continue on. Now we're at 20,000. These little regions are nothing, but eventually we'll hit a big jump. These are still small. Where's the, I should highlight the size. Yeah, it's still small. Size. Why can't I see it? Region size. This one. Okay, stop unhighlighting. Still small. It's coming soon. There's going to be a great big jump. Small. Oh no, F. Still small. F40. Now that's big, but it's not very big. 6, 7. Where are we currently? 16 with 4 zeros plus 6. I don't think we're going to get anything. No. Now we got a big one here. AB with 3 zeros from 180. I think the next one we're going to land in a module. Is that current position? No, not yet. I don't think. Takes a while. Okay, now this is a big one. This is 10 times bigger than the other ones, which leaves us at, now that's getting close to 40,000, right? I don't think that we're there yet. 3B, and I don't know what these little regions are. If they don't correspond to any module, this is not returning anything. C, Yeah, another, oh, 5,000. Okay, oh, 5,000. Size. So with all these tiny little regions. Oh, new one. Okay, this one's gonna do it. Oh no, almost. Hey, it says ACTX here. I wonder if that has to do with ActiveX. Sometimes you find funny things in these blocks. MZ. Okay, now I know what this one is, right? MZ stands for what's his name? The guy who invented the format for the portable executable header. Work for Microsoft. Mark Zimmerman or something like that. That's our program. I just want to find out what that name is. Curious. That's one of those things that'll win you at Trivial Pursuit, you know. Very critical information. MZ. I should have put wiki. Come on, where is it? Probably staring at it. It's the initials of a human being. Mark. Oh, here it is. Mark is I don't know how to pronounce that. Zabilski. There you go. MZ. There's an MZ at, strangely, at 40,000. Okay, and that's our next one to look at. Now this thing is not going to return 0, turns out. It didn't. It's starting to write out a path here, and you can see. But we don't care about that. All we want to do now is assign this variable, which is a persistent variable through the loop, to some number. Okay. The allocation base of the region, of this particular region. We need to remember that number, and that number happens to be this, 400,000. Now I add the region signs, and the question is, have we gone beyond the thing passed in? Not yet. Add the next region. Now we are beyond it. Right? Okay, now the last H instance that we found before we jump past the pointer we're looking at would be the module where that pointer is in. The assumption is that the pointer, in fact, is in from some module. Could be a bad assumption. And perhaps I should set this to null when we get to, every time we get to a new region. Not when this thing returns 0, you don't know anything. Well, anyway, go back, and that has returned the address of our program. The program is in memory. It should say in the autos. Okay. Now I call get module handle of null, which is a thing that returns me the address of where my program is located in memory. And that, again, that's an operating system call. So these two things will be equal, and so therefore quit. Alright, now I'm going through that thing that I explained before. I want to find out that magical address. In fact, do I need to do this here anymore? I might not. See, I didn't have this function before, and then I implemented it, and here I am. I'm doing it again. Right. This whole calculation from before, and in fact, this function shouldn't even be public. It should be private. It should be a private function. Now, anyway, so this really is the same as calling. What was it the same as calling? Passing in return address. Okay, so it's address of caller of you. Right? So I don't need this. In fact, I don't even need this because that thing will also checks for this condition. Right? It does the verify. It checks if we can read the memory. I guess it doesn't tell us if it's. Okay, we could leave this test in, but all this is doing is address of caller, same code. So I'll remove that. Actually, sorry. I'm stepping through this only to show you how to do a stack walk, because we don't need to do the stack walk, as it turns out. What I'm looking for is if the address of any caller on the call stack is equal to the address of the function that called this function, right? If that happens to be the case ever, then I'm going to return true. And in this case, it's not going to happen. We're going to hit where are we currently? This address. Main. See, we're looking at main now. We're almost out of the program. Now we've jumped out of the program. The address, well, it's being done on the stack, so you didn't see what the value was. But I traced it out. I'm going to trace it out here. Return address number 7 is in kernel 32 DLL, right? So therefore we hit a dead end, and so we didn't find the caller on the stack, and so therefore the caller is safe to proceed with running the default constructor for the outer class. See much time not used. long time. However, I realized something just earlier today, that this isn't a correct test, because it's not 100% guaranteed, because I can't imagine every possible scenario wherein we might find that function on the stack, right? It could be that the outer class's default constructor might run down and find some code that constructs another object of its own type, which would put this function init outer on the stack, but for a different object. You see what I'm saying? And it would be wrong to return in that case. In fact, we should know exactly when to return. And I'll also explain this and show you it very quickly, and then whoops, click. Delete this. I saved the other picture in a text file. Actually, this picture is not exactly right. It should be like this. It doesn't, I meant to mean it passes, it comes back. It doesn't go back to here, I'm already in there. Right? So in order to see if recursion has occurred, we know exactly where the recursion would be detected, right? This thing, outer, calls our default constructor directly. There's no intervening functions ever, never would be, which then calls this, right? So the number of, if we go 1, 2, 3 steps back and find our function, that should be enough to say that we've recursed. So I'm saying that we can change this function. It'll be more clear maybe when I write it down. Callers, caller. Now I can use this thing and just put 3 here. If those two are equal, then we're in a recursion. I believe that should be, I think I got the number right. If it's not 3, it's some other number. That's all. We shouldn't be searching further back than the amount of function stack that we know just by the way that constructors work. Now what have I got here? Something wrong. Semicolon. I just commented the semicolon. I did. Now don't tell me that this thing returns a capital boom. It's from some pretty old code. I can fix it. Syntax error, semicolon. Where's the semicolon? Oh, I got too many. I gotta fix this one thing. Operator. Yeah. That should be small. Okay, fixed. When this code was written, they didn't have such things as lowercase bool. This was in the DOS days, when, well, not DOS, but when DOS was still a big thing. The compilers hadn't added this keyword, this special type called bool. So I'm just going to put a breakpoint here. And that should be it. We don't need to do the walk. But I wanted to go through the walk and also explain how this AddressToHinst works. You may not have understood, but you can always replay the video and see if you get it the second time. Now they shouldn't be equal the first time through. 70 and 20, they're not. They should be equal this time, and they are. Okay, so second time through, the third one back. If you look at the call stack, right? 1, 2, 3. All right, jump back 3. That puts me here. It's actually, this is jumping back 1. This is jumping back. Sorry. This is jumping back 0 times, 1 time, 2 times, 3 times, right? With the 0 as argument, that's a single backwards jump. And that's always going to be the case because this init outer invokes the default constructor directly, and the default constructor is something that doesn't take any arguments, and so its invoking of another constructor would not involve anything else in between, right? The thing that I won't have the chance to show you, unfortunately, is about the order. What happened was I was getting memory leaks, okay? The reason I was getting memory leaks was because my default constructor was overwriting things that had already been set, okay? For example, here I'm setting this word unchanged. In the actual default constructor, and if I made the mistake of putting this here string that's being set there down here, I'm going to get a memory leak. Not only will I get a memory leak, but it won't retain that value. I'm not printing it out anywhere. Oh, I am here. Well, I'm going to run it without printing anything to show you the memory leak. The reason it's a memory leak is because the order of construction is not the order that things are listed here, it's the order things are listed here. So therefore, it would be wrong for me to put these over above this thing, because for these other constructors that set those other values, right, those values are going to get trashed when the default constructor gets entered and wipes out all of the, reinitializes everything, okay? However, if you have something in the default constructor itself, it should appear before this thing, this def tour. Just let this run, and I got a memory leak, okay? It's the word unchanged. Why is it the word unchanged? Because that's being initialized here. You see why the memory leak report is helpful. It can help you locate a bug like that, which has to do with the order of initialization. For one thing, the fact that the order depends on the way these things are laid out, and not the way these are laid out, is important. I'm not going to get a memory leak now, and the reason is because this string got constructed and then my function got entered. You see, the order has to do with declaration, and it was retained. Okay, here I've printed it out. The string. A string that is initialized in the default constructor, but look at how I'm making these objects. There's no default constructing anything. All kinds of crazy things are happening. Okay, that's enough. Hope you enjoyed that. And next, I'm going to show you my idea for the RPC client. See you.